In this video, we're going to see the snapshot object, but with a slight modification. So this is the wait-free snapshot algorithm you've seen in class. So you have this array of registers, and its position in this array contains a value, a timestamp, and a copy of the array of the values. And then you have the update operation. It increases the timestamp first, then it performs the scan, and then it stores this triple inside this inside the array, where again I corresponds to the identifier of the process. And you have a scan. The scan, what does it do? It first performs a collect, and then it enters this loop. It collects again. If what it collected is the same as before, then it just returns here. Then it tries to see if there was something that it read before that has been changed at least twice. So the timestamp stored in this element in the register array has been modified at least twice. If this case, it returns the copy of the array of values contained in the array. If not, the loop repeats. So this is a wait-free implementation. So what we're going to try to answer here is whether this too is really needed. And in order to answer this question, in order to see if this is really needed, we're going to try to see what happens if instead of 2 we have 1 here. Would this algorithm still be a wait-free linearizable snapshot object that's correct? Naturally, as you probably can guess, the fact that it was 2 there, it was for a reason. And probably with +1 it would not work. So in order to show that this would not be a correct snapshot object, a correct wait-free and linearizable snapshot object, we have to find a counterexample where linearizability is violated. So let's see this counterexample. So consider this execution where we have 3 processes. Processes P1 and P2 perform updates. Process P1 writes 1 and process P2 writes 2, while process P3 performs a scan. First, notice that the update of process P1 takes place before the scan of process P3 takes place. Okay, after saying that, consider that update 1 performs the actual write at this point. So this is the point where it's going to write to this array, let's say 1, 1, and then the array of values. And now consider that the update by process P2 takes place here. At this point it's going to write to 1, 0, 0, 0. And it's going to write 0, 0, 0 because the scan of this update operation takes place before the update by process P1 takes place, which is here. Okay, now let's see what the scan would do. The collect here takes place before the write that was performed here by process P2 and after the write that was performed by process P1. So it's going to read back, let's say for register 1, it's going to see 1, 1, 0, 0, 0. For register 2 and register 3, it will read, let's say, back the initial values. Let's say it was 0, 0, 0, 0, 0. Then what we have is the update by process P2 takes place here, and then we have a second collect by the scan operation. And now this second collect would read the exact same thing for register 1, but for register 2, it would now read 2, 1, 0, 0, 0. And the timestamp is 1, and before it was 0. So what this scan would do, it would return the array of values that are contained here, which would be 0, 0, 0. Naturally, this result here violates linearizability, since the scan takes place after, as we said at the beginning, the update by process P1, so it should definitely return 1 as the first element of the array that it scans. So this problem was again given in an older final exam some years ago, and it shows again that even a small change in an algorithm can actually violate its correctness. So it's really important to be careful when we think about this stuff.